Welcome to CyberXplain channel. Today we are going to discuss foundational security for machine learning systems. Hey everyone, welcome back to CyberXplain. Today, we are diving into something super hot, foundational security for machine learning systems. It's not just about traditional IT security anymore. ML brings its own unique set of challenges and attack vectors. Ever wondered why securing an AI model is different from securing a web server? It's because we are dealing with sensitive data, complex algorithms, and powerful models that can have real-world impact. We need to think about how data flows, where models are trained, and who can access what. Let's peel back the layers and see how we can keep our ML systems safe and sound. First up, let's talk about the bedrock of any ML system, your data. Just like you wouldn't build a skyscraper on a shaky foundation, you can't build a reliable, secure ML model on compromised data. If the data fed into your model is inaccurate, incomplete, or worse, maliciously altered, your model's predictions will be garbage. This isn't just about poor performance, it can lead to biased outcomes, incorrect decisions, and even security vulnerabilities if the model learns from bad inputs. Think about a fraud detection model trained on data where malicious transactions were intentionally mislabeled as legitimate. That's a recipe for disaster. So, how do we ensure our data is trustworthy? Enter data validation. This isn't just a one-time check, it's a continuous process built into your data pipelines. We set up rules to verify data types, check for missing values, enforce expected ranges, and ensure uniqueness where required. For example, ensuring customer IDs are unique integers, or that an age field falls within a reasonable range like 18 to 99. Tools like PySpark or Pandas allow us to implement these checks programmatically, catching anomalies before they even reach the training phase. It's like having a bouncer at the club, making sure only valid data gets in. Let's apply this to our sensitive customer churn prediction model. Imagine we are ingesting customer demographic data, billing history, and website activity. Our data validation pipeline would first ensure that every customer ID is unique and not null, because a duplicate ID could skew our analysis. Then, we'd check that the payment_status column only contains expected values like paid, late, or cancelled, and not some gibberish. We might also confirm that the last_login_date is actually a date, and that contract_length_months is a positive integer. These checks catch errors early, preventing bad data from ever touching our model. Now for the scary part. What happens when data validation fails or is bypassed? This opens the door to data poisoning attacks. A malicious actor could inject subtly altered data into your training set, causing your model to learn incorrect patterns or biases. For instance, they might intentionally mislabel a segment of high-value customers as low churn risk to manipulate business decisions. Another risk is a simple integrity breach, where data is accidentally or maliciously corrupted, leading to completely unreliable models. These attacks can be hard to detect, often only surfacing much later through poor model performance or biased predictions. To combat these threats, we need a multi-layered approach. First, strong access controls, ABAC, on your data sources are non-negotiable, ensuring only authorized personnel and services can write to the data lake. Data encryption, both at rest and in transit, protects against passive eavesdropping. Implement robust, automated data validation pipelines with clear error handling and alerts. Data versioning helps you roll back to a known good state if an issue is detected. Finally, cryptographic hashing of data at various stages can verify its integrity, ensuring no unauthorized changes have occurred between processing steps. It's all about building trust throughout the data lifecycle. Moving on from data, let's talk about where the magic happens, the model training environment. This is often a highly privileged space, accessing sensitive data, consuming significant compute resources, and ultimately creating your valuable intellectual property, the model itself. If an attacker compromises your training environment, they could steal your sensitive training data, inject backdoors directly into your model, or even leverage your expensive GPU compute for their own malicious purposes, like crypto mining. It's like leaving the blueprints to your secret sauce in an unlocked room. To secure these environments, isolation is key. We typically achieve this through network segmentation, placing training clusters in private subnets within a virtual private cloud, VPC, with strict ingress and egress rules. Containerization using Docker and Kubernetes is fantastic here, providing process-level isolation and reproducible environments. Ideally, training instances should be ephemeral, spun up only when needed and torn down immediately after, minimizing the attack window. Managed ML services like AWS SageMaker, GCP Vertex AI, or Azure Machine Learning also offer these isolation capabilities out of the box, simplifying our security posture. For our customer churn prediction model, we'll configure its training environment using AWS SageMaker. The SageMaker training job runs on an instance provisioned within a dedicated, private VPC. This VPC has no direct public internet access, and all traffic is routed through a NAT gateway or VPC endpoint to specific, approved services like S3 for data. The SageMaker execution role itself is granted only the absolute minimum permissions needed to read training data from an encrypted S3 bucket and write the trained model artifact back to another secure S3 location. This strict setup minimizes the potential for unauthorized access or data exfiltration during training. Despite isolation, threats remain. A common attack vector is the supply chain. What if a data scientist accidentally uses a malicious open-source library that was subtly backdoored? That library could then exfiltrate data from your training environment or inject vulnerabilities directly into your trained model. Another risk is credential theft. If an attacker gains access to an engineer's credentials, they could directly compromise a running training environment, stealing data, modifying code, or deploying their own malicious models. Think about the SolarWinds incident. Similar attacks can target ML dependencies. To mitigate these, we need a defense-in-depth strategy. Start with hardened, trusted base images for your containers, ideally scanned for vulnerabilities before use. Implement software composition analysis, SCA, to scan all your dependencies for known vulnerabilities. Code signing for internal libraries and model artifacts adds a layer of trust. Network isolation, as we discussed, prevents unauthorized communication. Runtime monitoring of your training jobs can detect unusual activity, like outbound connections to unexpected IPs. And remember, regular security audits of your training infrastructure are absolutely vital to catch misconfigurations. Now, let's talk about access control and permissions, which are complex in any IT system, but even more so for ML. An ML project involves a dizzying array of resources: raw data, processed data, training scripts, compute instances, model artifacts, inference endpoints, and logs. Different team members, data scientists, ML engineers, data analysts, security auditors, need varying levels of access to these resources. Granting too much access opens the door to abuse, but too little can stifle innovation and productivity. It's a constant balancing act to ensure least privilege without creating roadblocks for your team. This is where robust identity and access management, IAM, comes in. In cloud environments like AWS, Azure, Entra ID, or GCP, we use IAM to define specific roles and attach fine-grained policies to them. These policies dictate exactly what actions a user, group, or service account can perform on which resources. For example, a data scientist might have read-only access to raw data, permission to launch certain training jobs, but no access to production models. Service accounts are particularly important for ML, as they grant permissions to automated processes, like a SageMaker training job that needs to read data and write artifacts. It's all about precision. Let's bring back our customer churn prediction model, and map out its access controls. Data scientists on the Churn analytics team need read-only access to the raw customer data stored in an encrypted S3 bucket. They also need to be able to create notebooks in SageMaker. The ML engineers, however, need read-write access to the intermediate, pre-processed data also in S3 which they'll use to refine features. Crucially, the model's actual training job, running as a SageMaker service role, gets very specific permissions, read from the processed data bucket, and write to a designated model artifacts bucket. No one user should have all these permissions directly. Continuing with our Churn model, ML engineers require permissions to initiate and manage SageMaker training jobs. However, they don't directly interact with the underlying compute instances. Instead, the SageMaker service role, which we configured earlier, is the entity that actually runs the training, accessing the data and writing the resulting model artifact. Once trained, the model artifact is stored in a secure model registry. Only a specific MLOps deployment service account would have the permission to retrieve a signed model from this registry and deploy it to a production inference endpoint. This separation of duties prevents one user or role from controlling the entire pipeline. What happens when access controls aren't tight? Overprivileged access is a common culprit in breaches. If a data scientist's account has write access to production models, an attacker compromising that account could tamper with or delete the model. Or, imagine a service account used for logging that also has permissions to delete data, a classic misconfiguration leading to privilege escalation. This means a low-privilege entity can gain higher-level permissions than intended. A famous example isn't ML-specific, but the Capital One breach showed how a misconfigured WF role led to broad access to S3 buckets, underscoring the dangers of excessive permissions. The primary mitigation is the principle of least privilege, grant only the permissions absolutely necessary for a role or user to perform their task. Consider attribute-based access control, ABAC, for more dynamic, fine-grained control based on tags or attributes. Regular access reviews are crucial. You need to periodically check who has what access and if it's still needed. Multi-factor authentication, MFA, should be enforced for all privileged users. Finally, comprehensive audit logging and monitoring of access attempts are your eyes and ears, helping you detect and respond to unauthorized activities swiftly. It's about being proactive and continuously verifying. Alright, let's shift gears and talk about model artifacts. This isn't just the final .pkl or .onnx file, it's a whole collection of valuable assets. It includes the trained model weights, the configuration files used for training, pre-processing scripts, evaluation metrics, and even the Docker images or environments necessary to run the model. These artifacts represent countless hours of work, proprietary algorithms, and encapsulate sensitive patterns learned from your data. They are the crown jewels of your ML development, and if compromised, they can lead to intellectual property theft, competitive disadvantage, or even system-wide failures if tampered with. Protecting these artifacts requires a strategic approach. We need to store them in secure, encrypted cloud storage solutions like S3 Google Cloud Storage or Azure Blob Storage, ensuring encryption at rest. Versioning is absolutely critical. You need to track every iteration of your model, enabling rollbacks if a bad version is deployed. Model registries, like MLO or SageMaker Model Registry, provide a centralized, managed place for storing, versioning, and managing model lifecycle. And just like with code, cryptographic signing of your model artifacts can verify their integrity and authenticity, ensuring they haven't been tampered with since creation. For our customer churn prediction model, once trained, the .pkl file, along with its associated preprocessing script and configuration, is uploaded to an encrypted S3 bucket. This bucket is configured with strict IAM policies, allowing only the SageMaker training role to write to it and only the designated MLOps deployment service account to read from it. We then register this model version in the SageMaker model registry, which automatically tracks its metadata, lineage, and approval status. Before deployment, an automated pipeline verifies the model's cryptographic hash against the registered version, ensuring no tampering has occurred. So, what are the threats here? Model theft is a big one. An attacker could steal your model, either for competitive advantage, intellectual property theft, or to reverse engineer it for vulnerabilities. Then there's model tampering. Imagine an attacker subtly altering your churn model to classify a segment of high-risk customers as low risk, leading to significant financial losses. Or injecting a backdoor that activates under specific, rare input conditions, making it hard to detect. These attacks often target the storage layer or the deployment pipeline, emphasizing the need for robust security at every stage. Detecting these attacks relies on vigilance. Regularly verifying the cryptographic hashes of your model artifacts against trusted baselines is paramount. Any discrepancy indicates tampering. Monitor your model registry for unauthorized modifications, unexpected version updates, or deployments. Audit logs from your cloud storage and model registry services are gold mines for detecting suspicious activity, such as unusual access patterns or deletion attempts. Implementing anomaly detection on these logs can help spot unusual behavior that might indicate an attack. It's about having tripwires at every critical point. To effectively mitigate model theft and tampering, always use enterprise-grade model registries that offer strong access controls and audit capabilities. Implement cryptographically signed model artifacts so you can verify their authenticity and integrity before deployment. Your MLOps CI/CD pipelines must include security gates, such as automated vulnerability scanning of dependencies and environment images, and integrity checks of the model artifact itself. Ensure immutable artifact storage where once an artifact is written, it cannot be changed. Finally, enforce strong authorization mechanisms for any model deployment requiring multiple approvals. It's about building trust into your automation. Finally, let's touch upon something often seen as a nice-to-have but is rapidly becoming a security essential: model interpretability and explainability, or XAI. We often talk about XAI for business reasons, like understanding why a loan was denied. But for security, XAI is about peering inside the black box of your model to understand how it's making decisions, not just what it decided. This helps us identify potential vulnerabilities, detect if the model is relying on sensitive features it shouldn't, or if it might be susceptible to adversarial attacks. It's like having an X-ray vision for your AI. XAI tools like Line, Local Interpretable Model Agnostic Explanations, and SHAP, Happily Additive Explanations, help us understand feature importance, both globally and for individual predictions. For security, this is invaluable. Line can show you which specific input features contributed most to a particular prediction, helping identify if seemingly innocuous data points are actually driving critical decisions. SHAP values, on the other hand, provide a consistent way to measure each feature's contribution to a prediction. By examining these, we can uncover if a model is inadvertently using highly sensitive PII, or making decisions based on features that should logically be irrelevant, hinting at a flaw or even a backdoor. Let's apply XAI to our churn model. Imagine we run a SHAP analysis and find that for certain predictions of no churn, the model is heavily weighting a feature related to a specific employee ID, rather than customer behavior. This could indicate data leakage or a backdoor where the model implicitly learns to trust inputs associated with that ID. Or, we might discover that our model is making churn predictions based on a customer_gender field, even though we explicitly tried to remove gender bias. XAI helps us pinpoint these subtle, potentially problematic dependencies, allowing us to remediate them before they become a full-blown security or ethical incident. The black box nature of many complex ML models is a security vulnerability in itself. If you don't understand why your model works, how can you truly secure it? This opacity makes models susceptible to adversarial examples. These are inputs that are subtly perturbed, often imperceptibly to humans, to trick a model into making an incorrect prediction. Without XAI, it's incredibly difficult to understand why the model was fooled, making it hard to defend against. XAI can help by highlighting the specific features or input regions that contribute to the misclassification, revealing the model's blind spots. The best way to leverage XAI for security is to integrate it directly into your secure MLOps pipeline. Before deploying any model to production, include an automated XAI security check. This step would analyze the model's explanations to identify signs of data leakage, over-reliance on sensitive features, or susceptibility to known adversarial patterns. Continuous monitoring of model explanations in production can also detect concept drift or data shifts that might open new vulnerabilities. By making XAI a mandatory security gate, you add a crucial layer of defense, ensuring that your models are not only performant but also transparent and resilient. And that wraps up our deep dive into foundational security for machine learning systems. We've covered a lot, from the absolute necessity of data integrity and validation to securing your training environments and protecting those valuable model artifacts. We also explored how powerful XAI can be, not just for business insights, but as a critical security tool to peek inside your models. ML security is a rapidly evolving field, full of unique challenges, but by applying these foundational principles, you'll be well on your way to building more robust and trustworthy AI systems. Keep learning, stay curious, and keep those models safe. Thanks for watching. Subscribe to the CyberXplain channel. See you on the next video.